So, welcome to the small introduction into SDR, software-defined radio on Linux. This has been coming a long way. Since quite some years, I have been asking others also on the TLUG mailing list around topics like this. And we have people in the group way better suited for this talk, namely Jim Titzler, but he's excused. He's living far away for not coming in today. Yeah, but this is it. I'm Christian Horn. We will mostly look into things we can do with just receiving something and today. And I'm not a lawyer, but I think this is pretty safe law-wise. If someone wants you to not understand something and participate in something, they usually scramble something and then you should walk away, like police or something. But I'm not a lawyer. Yeah. If you want to send something nonetheless, then you might need one of these call signs. So anyway, electromagnetic waves, we are sending these every day. We have our mobile phones and we have wireless and we have Bluetooth, we have all kinds of stuff. Why is this not sufficient? Sometimes because with wireless or with the mobile phones, we are using devices which are fabricated and have seen thorough checking by various instances and Tokyoku, and they have been declared safe to use by normal users. And if you prove that you can understand the implications of sending out electromagnetic waves with more power and on more frequencies than the normal devices are allowing you, then you can prove this with an exam. You get a worldwide unique nickname, and then you are allowed to do within certain ranges a bit more. Yeah. So this is our agenda. Who am I? I will skim over this. This section is anyway only here because I was kind of an earlier version of this presentation giving at the local ham radio club. And these guys are, so it's mostly the same contents. Here you are like, yeah, it's clear that you are using Linux with this wireless technology, but what is this radio stuff? And at the ham radio club, these guys were, yeah, the radio stuff is clear, but what is this Linux stuff? This is the difference between the two audiences. We will look at the plain old radio and we'll try to translate how this is then done with the software-defined radio work. We will then look into two softwares in detail. I will introduce a bit of hardware and how to talk about how to set up. Yeah, most of you know me anyway. So, what's a radio anyway? And how is this old radio you have in your room translating to something like this? We have an antenna here. And the antenna is for receiving electromagnetic waves and for translating them in the end into something we can hear. That's the goal of our radio here. The loudspeaker, of course, is responsible for making the air vibrate and giving us something to hear. We have these scales here. So this is an illustration of frequencies. We can use our frequency knob to tune in a frequency. We see here multiple scales actually. And with this band select, we can choose one of these scales. actually, we could also imagine these different scales as one long scale and then use the knob to move the exact frequency we want to tune in on this long scale. This would be the same. Yeah, and eventually we have there a mode select, FM and AM. And while you practically know what it's good for, so these are different kinds of rays on how what we can hear, this signal is getting modulated on this received electromagnetic wave. We will talk about low frequency. In our setups, we mean with this something between 20 Hertz and 20 kilohertz. This is typically the range we are also, our ear are capable of hearing. We will talk about high frequency. And in our context, this is used to talk about the frequency with which the electromagnetic waves we are receiving are transmitted. Right. So basically, when we listen to a radio program, we are receiving electromagnetic waves. What is coming out is the low frequency. So we have a procedure which is called modulation. So we want the information we want to hear, and it's the medium for transmission is the electromagnetic wave. And having it backpacked on the electromagnetic wave is called the modulation. And in the end, what our radio is doing then, the demodulation, making this hearable for us again. And our mode select is then allowing us to choose between two different modes of encoding the low frequency in the electromagnetic waves. Okay. What's then the more modern version of this radio? With the software-defined radio, we would be looking at typically this setup. We have here an antenna. We have our SDR device, our software-defined radio device. We have our laptop. And one of the two applications I will introduce, it's just an X-client application running on the laptop. The second one is running more like a service. It's a daemon running. It's starting to listen on one TCP port, and it can be accessed with a web browser. The web browser could be running directly on the system. It could also be running remotely somewhere over the internet or on your local network. Let's talk about frequencies. There is a serious bug in this illustration, which I have not yet fixed in this version, unfortunately. I will talk about this in a minute. So the most important thing here is our frequency. I was already saying, so we were looking at the frequency with these three scales on this classic old style radio, but we could also visualize the frequency as just one long line here, and then we have several marks for these frequencies. So typically we are calling frequencies in the area of 30 kilohertz to 300 kilohertz low frequency. Also even, low 30 kilohertz, as we just learned, when it's transmitted with vibrating air, we cannot even hear this, but in our context here, we are calling this low frequency. We are looking here higher, between 30 and 300 megahertz. This is what we call very high frequency. We have here ultra high frequency, and so forth. The other line here is the wavelengths. And the wavelengths and the frequency, they are directly related. The higher the frequency, the shorter the length of a single wave. So we see directly here, if we have a signal with 30 megahertz, then the wavelength is 10 meters. And to the left, our wavelength is getting smaller, longer, and to the right here, it's getting smaller. And this is a bug actually, well, the arrow should be on the other side. I'm sorry. It's fixed in your version. We will mostly talk about two software-defined radio devices, which are called RTL-SDR and HEC-RF. RTL-SDR is this small guy here. You can get this with simple antenna like this for around $80. Why is it so cheap? Devices like this were initially produced for DVB-T, digital video broadcast terrestrial. So some maker made devices a bit like this with a chip, with exactly the same chip. And someone said, wouldn't it be nice if we could take the frequency range open and use it for software-defined radio? This is what happened, and this is why this guy here is so cheap. This bigger guy here is the HEC-RF. And we see directly here that these are spanning different frequency ranges. They are both starting with 30 kilohertz, and then the RTL-SDR is going to 2 gigahertz, and the HEC-RF is good for 6. And there are other differences too. This guy can only receive, so you are safe without this passing the exam. And this guy here can potentially also transmit. What's happening in all of these frequencies? Just to call out a few things which are happening. We have VHF, which is popular for radio. We have here a first small piece of what is used for wireless. And we have then here also a stripe, 2.4 gigahertz, 6 gigahertz. This is the newest one, also used for Wi-Fi. And then we have all kind of other pieces which are sometimes free for everybody to use with devices which have a proper label from the authorities. So they have been checked for security. We have also here pieces in like our mobile networks, of course, and so on. Mobile networks are then also a few stripes in here. And the fun with mobile networks is, and already with Wi-Fi actually, is that all countries are doing this differently. All of them have the authority about their frequencies. All of them do then go to the mobile network providers and have them pay money. And then the providers get different stripes in every country, which means if you are looking for a new 5G phone, you could, well, just say YOLO, I'm just buying one. Or you could go onto the internet and then see which 5G stripes actually your phone is able to manage and what in your country is spoken. We have this area here for radio. We have here then also something like the Japan time signal. And by the way, the differences between these frequencies are also huge. Which means, for example, popular for radio means the transmission, the propagation of the electromagnetic waves in this area here is mostly as far as you can see. So we have the globe, we have a station, and as far as it can basically shine, it can be received, plus something like 10 degrees or something. If we look at, for example, the Japan time signal in 30 kilohertz, 40 kilohertz area, this is very different. We have just, so for Japan, we have basically 2 transmitters for this. And you would also want to receive this if you are on the attic and also in the basement. So yeah, on these frequencies, you can also receive this in your basement. On the other hand, these transmitters are also extremely strong and inefficient with the electrical power they are putting in compared to the damper, the electromagnetic waves they are getting out. This is also due to the low frequency they are operating on. Anyway, we will look at 2 pieces of software. Of course, there's everything under the sun around, and these are 2 examples. GQRX is a typical X application you would run, and which is a bit like the old classic radio, with just the processing parts from no longer being in the radio, but being done in the computer. And OpenWebRX is a bit more complex. It's meant to be run as a daemon. It will contact the SDR device. It will then start to listen on a TCP port, and you can, with your browser, connect to the port and can also access frequencies and access the functionality of your SDR device. Because this has basically network capability built in, you can also have this opened up for others. Right, we were talking about modes, decode modes. So modulation was this way of bringing this, what we want to hear, or the other signal onto the electromagnetic wave. There are more than just AM and FM. Others are called, let's just take them as names for now, near FM, SSB. Right. Besides analog, besides something we want to hear, we can also talk about digital modes nowadays. This is something really cool. Some of the most interesting things are ADSB, and these are the signals which are sent out by planes. And you can also already try this out with this $80 device here. FT8 is something which ham radio operators like to do. So you would be sending out this signal for yourself, and you would try to see how far you can get. And you can also, with the other station, try to see if the other station, not only you hear them, they hear also you, and you can exchange reports and messages, of course. Let's talk about the most classic mode, actually. The most classic way of transmitting something is CW, or Morse code. And with this, of course, you are using typically your ear. And this is simple in that it's like a buzzer, and either we hear a frequency of 300 or 600 hertz, or we do not hear it. So when you listen to this, you just have to distinguish between 2 modes. I hear something, or I do not hear it. And with this, you can either do short or long transmissions of this tone. And with this, you can fabricate whole alphabets and get across messages. Anyway, the recommended hardware, we will, of course, use Linux. Something older is okay. 4 GB of memory is nice. Raspberry Pi 4 is nice. SDR support. So the software has, of course, to be able to talk with the SDR device you are using. There is not like one single interface where every SDR would talk to and every software would on the other end want to talk with this interface. This doesn't exist. Our two softwares we will talk about, they both support both of these devices here. This one here, the RTL SDR, so the versions 3 or 4 are the current ones. Some people still buy the version 3 because some obscure software can still not deal with the 4. This is the hardware version 4 I'm having here. HackRF is an interesting case. So this is a completely, so the design here is not open. It's dirt cheap, but the design, the hardware design is not open. The hardware design of the HackRF is open, and the original is sold for around $400. This here is a cheap China clone for $130, which is okay functionality-wise. But I haven't dared to update the firmware of the official one to this one. Maybe I'm ending up with just a brick, so no, let's not do this. What's else interesting when we compare SDR devices? This is actually the not as cool comparison. Let's look at this one here. This is a crowdfunding project. Anyway, the most interesting piece is they all have this kind of comparison for their devices, which helps us. Our RTL SDR is this one here, and our HackRF1 is here. And we see the important or the most interesting attributes which we might be interested when buying a SDR device. We see here how the interface is always how the device is communicating with our system. This is important, and we see actually even the newest version of the HackRF1 is also just using USB 2. Another interesting piece here is the RF bandwidth. We have not talked exactly about this. We were looking initially at our classic radio, and it's clear and easy for everybody to understand that you would just want to listen to one radio station at a time. Why would you want to have more? Well, with SDR we can have more. We were looking at this frequency spectrum, and actually these devices, they are not listening to just one single frequency. They are listening to a range in parallel. Of course, I would not want to listen to 20 radio stations in parallel, but we can monitor how much activity is going on in all of these frequencies and can then say, and I want to listen on in this one. This is what SDR devices are helping us. And this RF bandwidth is then how wide is this shape, how much frequency can we cover at a single point in time. And then you see here that actually the RTL SDR has one of the smallest ones. And we see that the HackRF1 is around 5 or 7 times as wide, which is already something good to see. We see here also something like transmitter channels, which is already telling us the RTL SDR is just for receiving, and the HackRF1 can be used for sending out. And we see also there are devices which can send out on 2 frequencies in parallel. Receivers, we can also basically have 2 of these bands if we want with some of these devices. Okay, and this is almost. Oscillator is one piece in our devices which is especially important for operation. So the stability of these here are parts per million. Stability of these is important. Yeah, but anyway, all of these are temperature controlled, temperature compensated, I think. Yeah. Okay, as much for the comparison. Antennas. We looked at this wide spectrum of frequencies. And guess what? Depending on what you want to receive, you also should optimize your antenna for this. Which means the time signals, this is just, have you ever seen one of these wall clocks with long antennas or something? Of course not, because in this frequency area there is just a small blob of metal which is capable of sufficiently receive this area. VHF, here we see often this kind of antennas. And also here it's worth to optimize that the length of our antenna is matching a quarter or the half of the wavelength of the frequency of the, the half or quarter of the wavelengths we want to receive. And the higher it gets here, the more you will see satellite dishes, which are then also directional. These antennas here, they have, of course, they are receiving from all sides signals with the same strength. And if you have a satellite dish, then you would, everything facing the satellite dish would be better received by you than something to the left and to the right, of course. By the way, the Yagi-Uda antenna had now anniversary these days. And it was developed, invented in Japan. So, yeah. How to set up? Quite easy. Setting up, Debian is a good default for this kind of software. GQRX is as simple as it could get, apt-get install GQRX software. OpenWebRx is a bit more complicated, so I'm actually talking here about OpenWebRx Plus, and there is of course something without, it implies that there is something without the plus, which is a version which has a fewer decoders. So you would receive signals in the same quality, but it would not be able to understand and decode as many signals as OpenWebRx Plus. Yeah, this is actually already the details. Let's try to look at this. Let's actually try like this. Does anybody have any certain wishes for what to receive? What would you like to receive? So a good default is usually to listen to ultra shortwave, to UHF radio. And actually there is something. We are inside a concrete box, but the tower is so strong. It's actually, so I was here selecting narrow FM. So we have a signal, we see some signal here. We are, like this graph we were looking at, we are having an increasing frequency here. We are looking here at 90.5 megahertz frequency. This is slower, this is higher, and we are at one point covering, looking at a whole frequency range. This is the so-called waterfall. We see over time then how strong the signals were a bit in the past. We see then here that we have some kind of signal, and we can just make guesses which kind of signal this could be. We can take educated guesses in this frequency area. This is probably a radio signal. And here, this module allows us to select which kind of modulation we suspect and what we want it to demodulate. These here are sideband modes, and here we have Morse code. And actually, wide FM would look likely for this one here. Yeah, bingo. Okay, it's not seeing the HDMI monitor as output, but anyway, yeah. Okay, so we managed. We managed to get a signal and to decode it. This is nice.
Do you have a time signal decoder? Let's try 30 megahertz.
Yeah, I was discussing this. How, hey, I want to see the stuff with time signal. Let me first stop this and go back here for a minute. It's an excellent question. I was discussing this. So how about this time signal? Can we tune down? No, actually it's too low. So it's not like our RTL SDR would be receiving. So if we have a signal of a certain strength over all of this frequency area, it's not like our RTL SDR would be strong enough and receiving it well everywhere. So towards the end, towards the start, the signal is the reception is worse than usual. And for the time signal, we are not sufficiently covering. Anyway, this is almost the area we could hear. So I got the advice I could look up an old style sound card and could use a long wire and could try to do some magic with this.
Why RTL can receive it like you don't have radio frequency strength enough to get to this long wave?
I think it's just not allowing me to select a frequency this low. It's as simple already. Here we at so, and this is 300 kilohertz is the lowest I can right now go here with the RTL SDR. Let me restart the. Let's have a look at the other software. So I was basically pulling away the access to the RTL, to the software-defined radio from this other software. So let's restart OpenWebIX and let's have a look at this here. We are looking at a web interface basically showing us the same. The thing with this software is we see here the frequency, and it's not like, so the software is meant to be accessed also by multiple people at the same time. And these, of course, have to stay within, I said, with this cheap guy here, we can just look at one frequency area at a time. And all of the visitors have to stay within this frequency. But they could listen to different radio stations or decode different signals in this area, of course. That would work. One specialty of the software is I cannot really tune to every frequency I can think of, and which the device is capable of doing with this one here. Instead, I have pre-selected areas here. I have one here which I have called ultra shortwave, and here we see again signals which look like radio, and then I have to turn on this. Yeah, great. So again, yeah, we have radio here. We can also do stuff like bookmarks here, actually. For the next time we are looking up something and wondering what the signal was anyway. So what is it I was doing with this? FT8 is one of these digital modes which is trying to see how far you can get. With this guy here, I can only receive, but on different frequency areas here, I did configure these as profiles, and I can then basically tune in and can see if I can receive something. The reception couldn't be worse than here inside of this building with this antenna just standing down, and of course we will not get in anything with this here. But this is the idea. You can create multiple profiles of pieces which are interesting to you, and then you can tune in. You can say, I want you to try to decode this signal again here as an FM frequency modulated signal, or as white FM, typically radio stations, or I think it's CW, it's Morse code. Please decode this for me. And then it will go around and will really decode this and write in clear text for the modes which it is capable of decoding. It will do the decoding for us. That's good. How is this looking like? What's this looking like for a really busy station? I have here actually what this was looking like for me. When was this? This was in summer at 30 degrees last year. And here we see I'm decoding FT8. So this is then what it can look like at the 7th floor of a mansion in Setagaya. And here we see decoded signals actually. We see then FT8 is not really, it's meant for low bandwidth, wide reception. So people are just saying, I'm this station and I'm addressing this station, and they are giving each other reports on how nicely they are receiving each other. This is typically the content of FT8. Oh, by the way, D-Star here is an interesting mode in that it's digital voice, but it's not like AM or FM, like analog encodings. It's really digitalized as we have in the mobile networks nowadays, and transmitted over the air. This is also a nice functionality from OpenWebRx. So just leaving this setup running for some hours, you could come up with something like this. The green stuff means in a certain area, 20 meter, wavelength 20 meter area. I was listening for quite some time and I have seen FT8 signals from these areas over the world. which is not too bad for this small antenna just deployed. Actually, I had also the idea of sending out something today for this presentation in Setagaya and having it received here, but it didn't work out. This here is interesting. So, receiving sensors. I know people who say I don't have on my balcony a temperature sensor because I'm running an SDR. I'm just looking at the 20 readings of my neighbors and I'm using the average of that. You can also see nowadays cars driving by and reporting the pressure of the tires via ISM readings and all kinds of things. Where was this actually? All right, so this was taken in Europe, right? Yeah, this was when I was in Germany. Oh, and this is ADSB, so airplanes flying above you and reporting where they are flying basically. So you can then directly click on any of these flights and see where these planes are heading to and this kind of stuff. This is the whole setup as I was using it. And yeah, one more thing. So this kind of the Open Web RX software is meant to not only be used by one person, but you can also decide to open this up to the world, and others are also doing this. And this is a kind of repository where people have opened up their nice setups. So this cute thing here, so this is Kiwi, is also a kind of software-defined radio. They are selling hardware together with and have a piece of software which is fitted nicely onto the hardware. One of the specialities is that they have from 0 to 30 megahertz all at once is what they are capable of bringing to the web interface. This is one of these systems. How can I now? Yeah. So this is what a really busy busy area can look like. You could then decide to scroll in somewhere. Actually, so these here are all radio stations. You could then say, I want to just tune into this radio station. What's this one? You could also say, I'm zooming into a certain area of the range here. Or let's zoom out again. And we see, let me mute this for a minute again. Yeah. The fun thing is, of course, the signals around here are not only voice and Morse code. So we have things like SSTV, pictures sent out. We have things like fax sent out, all kinds of stuff. Let me give you an idea looking at this here. So this kind of software can also decode Morse code directly for us. We have fax decoding. What is it doing if I'm enabling this? Indeed. So actually the owner here has set up directly that he is now jumping to a frequency where typically faxes are being sent out. And now what we are receiving is directly mapped into a received fax. Quite nice. Quite nice, quite nice. What's this here? Oh, okay. So this is weather related. Snowstorm, huh? No idea which kind of weather they have here. But you could apparently choose between frequently. So I know in Germany this kind of service is used still by ships to receive what the weather will be like in the next hours. And I guess they have here set up some stations which you can directly just tune in and then try to decode what they are receiving. Yeah. SSTV, would be hard, of course, to. SSTV is this thing of sending pictures over the air. Also, a nice kind of hobby for many people.
But you would need a receiver with some decoder to watch the TV itself, no?
You would start to receive the signal, and you would, for some point, need a decoder running to evaluate the signal until the full picture has been transmitted.
No, I mean the TV which is encoded, not only modulated for radio transmission, but also encrypted, no?
So typically, depends on the frequency, depends on who is sending something. If stuff is sent out on ham radio frequencies, then by rule everything has to be in the open. And STV typically is also in this area of everything open. Indeed. One more thing is, what can you do if you pass one of these exams and are also allowed to send out? What are ham radio people doing? They are doing RACTU, so using this to directly talk over the air with others. There is something called DXing. I try to get as far as possible. Many have then a nice world map and try to get all of the countries. And North Korea, for example, is one of the countries really hard to get to. Sometimes there are also islands which are not always populated. And then ham radio operators are collecting money and sending people there to send from there for some days so they can check that mark. It's also kind of a hobby, I guess. There is summits on the air. If I manage to learn Morse code reasonably, I'm planning to do this. So people go hiking, they are setting up just an antenna at the summit, and they are then trying to make connections, and they are getting points based on how far away and with how many stations, remote stations, they are making connections. A bit in the same vein is parks on the air. Of course, you do not have to climb somewhere for this. Earth-Moon, Earth communication. People are then not using like this antenna, which would be sending out to all directions. They would be using a satellite dish. They would point it at the moon. They would hope it gets reflected somewhere. And somewhere is also pointing their satellite dish to the moon, and then they can communicate. It's an interesting hobby. Who wants to take a guess what EVE is?
Venus, I guess.
Yeah, I have no idea which kind of gears they were using.
That depends on the frequency, actually. The gear is not so different from the moon one, but you have to choose the narrow bandwidth which can be reflected from the Venus atmosphere.
So chances for this to succeed are of course lower than with EME. We did not talk about how much power is the devices are putting out actually. This is usually just in milliwatts or watt area. And with license, you could put out something like a kilowatt on certain frequencies. So this depends on the frequency, and you need to follow, of course, strict rules. This is like the maximum you could be putting out if you're not violating anything else. So Hamnet, there are setups of like alternate internets for interconnecting basically ham radio operators for communicating with data without any ISP. There is a nice podcast. I can really recommend this. This guy from Israel is talking for 45 minutes with ham radio operators who are telling their story and what they are doing and which of these interesting things they are most fascinated with. Ham radio frequencies for Japan. These are listed here because these are, of course, a nice goal or a nice area for spying on or for listening in, for tuning in with these RTL, SDR or the HEC RF, for example. Yeah, and many more things which can be done. Any questions or comments? So,
is anyone doing any radio astronomy stuff with these, or no?
yeah, so radios, you mean pure, this is more receiving, but they are using obscure frequencies. I would think, yeah, so it's the kind of equipment you would use for this is similar, I think. You would use much bigger dishes, and it's probably a related hobby and a related technology area. I would not be surprised if much of this gear is also used for radio astronomy. And we have also, so for example, if you are acting in the highest frequency areas, something like 10 gigahertz, so you might have noticed the cable I'm using to the antenna here, this is a coax cable, which is it's not like two single wires. It's something which is meant to deal especially smart with the high frequency on the cable. If you are dealing with 10 gigahertz and above, then we have actually also already set ups where we have like a satellite dish. We have an LNB, something for receiving. And in this LNB, we are down converting this to something where a cable which we can pay is then transporting the signal away. So this kind of smart stuff is done all the time in this area of technology. Oh, and by the way, this conversion down by itself is already cool, but actually the power to, so the DC to power to do this conversion is also coming via this same cable in. This is called bias T and is something really cool. Oh, and by the way, usually this DC, so this current you're supplying to the LNB for doing this conversion, usually these are two areas of voltage, so 6 and 12 volt. And if you swap between these, then the LNB starts to receive with a different polarization. So frequencies, how to explain this? You could, polarization is like a direction in which the field is directed. So this would be here vertically polarized. Polarized signals would be nicely received by this kind of antenna, and this would be horizontal. And then there are also circular into both areas. So these four kinds of polarizations are distinguished, and ideally the sender and the receiver should match each other. So in switching then the voltage of this power supply to the satellite dish, you can also then suddenly receive in the other circularized polarization. Fun stuff like this is everywhere in the ham radio technology area.
are people using arrays or doing anything interesting with arrays of works? I mean, that seemed to be something that sounded interesting about potentially this. If you get people on different sides of the earth with dishes, then effective.
Yeah. So this here would be an antenna which you would use and receive something from everywhere. And if I were to use this for sending, the signal would be sent out to all areas equally. This illustration here is, of course, the Yagi-Uda antenna, which is directional. So the signal here in this area will be strongest. And if I send something out, what's received here or here or here will not be as strong. The more of these radials we are using, the stronger the focus, the so-called gain will be of this antenna. On top of this, people can use then 2 or 4 of these antennas, put them together to a so-called array to have even better focus. And all kinds of stuff is done.
Anything along the lines of multiple SDRs, like so, for example, have them working in sync? Or?
There are people who are, for example, using these guys and just to have wider range of frequencies covered, of course. We have also SDRs, which are composed of, I have seen one, which is composed of five of these stick antennas. And basically, if you have a signal based on where on these antennas this was received first, it's then starting to use this for in computation of from which area this signal was coming. Yeah. So combinations of all of these are used for all kind of fun stuff also. Your first question reminded me. So we had the Chaos Communication Congress end of the last year, and we had the Ham Radio Club in Berlin, who were talking with a spacecraft from SpaceX. And they did 45 minutes of presentation on this. They got it, so the spacecraft is moving around the world. They got a 10-minute time window in which they had to talk with these guys. They were setting up, and they had this like 1 or 2 weeks in advance, and they were setting up 3 setups. Actually, their best antenna setup was 4 Yagi antennas, right-wing circular polarized, and they could direct this everywhere in the sky, of course. The second one is then just something as simple as this, which is receiving from everywhere. And then the third one was like quad antennas, 2, and they could also directionally point this at somewhere in the sky. And actually the strongest one, so the setup of 4 Yagis, this was right circuit, and this was the one which wasn't work anyway for this, because apparently the spacecraft was using left circular polarization. I can really recommend the original speech presentation is in German, but the Lingua team did an English translation. And yeah, highly recommended this one.
Do you mind?
Yeah.
Do you know if there's like any kind of like tools we can use? Like maybe we're curious about like what's around us, and we want to like catalog that and kind of see if there's any changes in maybe the radio environment. Is there anything that they can do that maybe automatically, something like that? So you kind of like keep.
Yeah. I know what you mean, and I cannot point you at something. I can say that this would be a really interesting kind of research. Also, in automatic classification. So what works relatively good is having SDRs look always constantly over all of their frequencies and say if something is received which is above a certain strength of a signal. What's bad is guessing which kind of signal it is, from where it's coming. All of this kind of classification would be super cool if you had this running in the background and then had like a pop-up and hey, there's something coming up. What's this there? And it's not there apparently. I guess military grade and equipment would they probably have the money and they are throwing this, of course, and they would be watching the frequencies all the time, I guess. One interesting hobby I was forgetting actually is there are people who are, so there is also, besides sending, just for listening, the Spectrum Monitor is a nice monthly magazine, electronically sent out. It costs money, but, and there was one interesting contribution. There is someone who is interested in the frequencies with which Russia's ships are communicating. So he is having a book and taking log of in which frequencies they are communicating. You can use then this kind of distributed receivers all over the world to try to make guesses and see if they are really there. And there's all kind of fascinating exotic pieces of this hobby.
Thank you.
Right.
Okay.
Question.